Hello and welcome back. In this video, we're going to derive some equations that are going to be useful when we're in a very specific case, and that case is constant acceleration. So the velocity changing by the same amount every successive second that it did the second before. So constant acceleration, remember, acceleration is the slope on the velocity versus time graph. So if the acceleration is constant, then the slope on the velocity versus time graph will always be constant. And of course, it's just going to be a line then if it's constant. So recall slope is just the rise over run. So the rise over run is going to remain a constant value. This would be a graph that would correspond to a constant positive acceleration. For the purposes of this derivation, it's not going to matter whether the acceleration is constant or negative. The equations are valid in either case. So this is kind of what a graph would look like. Remember that acceleration is rise over run on the velocity versus time graph. So that's some final velocity minus some initial velocity over a final time minus initial time. We're going to make the initial time 0. And most of the times that will be the case that the initial time will be 0. So we can write then the acceleration as v minus v naught over t. So here is our velocity versus time graph again, an initial velocity at time t equals 0, final velocity at some final time. And so we can look at the average velocity on this graph, the average velocity. And this is just from math. Anytime you have a straight line, if you want to find the average on that line, all you do is add the two endpoints and divide by 2. It's true for any line. So this is v plus v naught over 2. So the average velocity can be written as just the endpoints summed together and divided by 2. And recall back from previous lectures that average velocity is also displacement over time. Remember, we're getting rid of that delta because t naught is 0. So this relationship right here is going to be pretty key in us being able to derive these equations for constant acceleration. And notice that this equation right here is only valid for the case of constant acceleration, because the only time you can say that the average velocity are the endpoints of the velocity divided by 2 is if the graph of the velocity versus time graph is just a straight line, which means that the acceleration or the slope is constant. So only true for the case of constant acceleration. And now we're going to take an equation. This one happens to always be true, but we're going to use it to combine it with this equation. And so the pursuant equations are only going to be valid for the case of constant acceleration. So I'm going to take this equation and I'm going to rearrange it. I'm going to multiply both sides by time so that I have v minus v naught isolated on one side, and then on the other side I'm going to have acceleration times time. So this is going to be one of the equations that's going to be useful. We'll call that equation 1, and we'll call this one equation 2. So equation 1 and equation 2 are going to be used together, substituting for one quantity in one equation and plugging it in for that quantity into the other equation to generate 3 more equations. So notice that velocity appears, final velocity appears in both of these equations. Initial velocity also appears in both of these equations, and time appears in both of these equations. So what we're going to do is we're going to take equation 1 and solve for v, then plug into equation 2. All right, so I'm taking equation 1 and I want to isolate v. So from equation 1, I get that v is equal to v naught plus a t. You're going to notice I'm going to skip some algebraic steps as we move along. Please fill in the pieces that I did not cover if you can't easily see them. Algebra is paramount to being able to do physics at this level, and this is a good practice ground for you to remind yourself how to do some basic algebra. So now I'm going to plug this into equation 2. So what does equation 2 become? So here is v. So instead of of writing v here, I'm going to write what v is equal to from equation 1. So I have v naught plus at, that's now my v, so plus v naught, and the whole numerator over 2, and that's equal to delta x over t. If I rearrange this equation, what I will get, and this will be familiar when you look in the book because it's expressed this way, is this form right here. So these two are the same equations. This is just rearranged. And this now gives us a third equation that we can use for the case of constant acceleration. So we took equation 1, solve for v, and then plug that into 2. So what are we going to do next? Let's take equation 1, solve for v naught, then plug into 2. Okay, so what do we get from equation 1 when we solve for v naught? V naught is going to be equal to v minus at. And now I'm going to take equation 2, and wherever I see v naught, I'm going to plug in what v naught is equal to in terms of va and t. So start off here at equation 2. I have v plus, boom, now I have v naught. Instead of writing v naught, I'm going to write v minus at. And that whole numerator now over 2, and that's equal to delta x over t. Rearranging this equation, we're going to get delta x is equal to vt minus 1/2 at squared. This I'm going to label as equation 4. Another equation that's going to be useful for the case of constant acceleration. So notice we're just starting off with these two equations, and we're just weaving them together to generate these other equations. So we've substituted equation 1 out for v, also for v naught. A doesn't appear in equation 2, so that's not going to be useful, but t does appear in equation 2. So I can take equation 1, solve for t, and then plug that into equation 2. So take equation 1, solve for t, then plug into 2. All right, so what does equation 1 become when we solve or isolate t? T is equal to v minus v naught over a. And so what does equation 2 become when I plug this expression for t in? Well, the left-hand side, v plus v naught over 2. The right-hand side, delta x, divided by t, and t is v minus v naught over a. Taking this equation and just rearranging it is going to allow us to express it as v squared is equal to v naught squared plus 2a delta x. This is going to be the fifth and final equation we're going to be able to derive for the case of constant acceleration. So these 5 equations, very useful for the case of constant acceleration, and these equations are going to be very useful when we study free fall, and that is the condition in which only the Earth's gravity is exerting a force on an object that is near the Earth's surface. And so this is going to be the case of free fall. And we will look at that and tailor these equations specifically to the case of free fall next time. But please remember that these equations are going to be useful anytime we have a case of constant acceleration. It doesn't have to be free fall. It just happens to be a very important case of constant acceleration. One last thing I'd like to point out is that equations 3 and 4, while they look similar, are indeed very different. In equation 3, it's the initial velocity that's important, and in it, that is required, and in equation 4 it's the final velocity that is important. And then notice also that you have a subtraction of the 1/2 at squared from equation 4 and an addition of the 1/2 at squared in equation 3. So different equations, these 5 very useful cases of constant acceleration. See you next time.